Now we're going to talk about the transition between a liquid and a gas. So here we have an illustration of water in a beaker. And like the quote at the beginning says, it's a wild dance floor down there at the molecular level. This is like a mosh pit, right? There's just people, molecules, just they're moving all over the place, right? They're swimming around, literally. Well, some of them may have movement in the direction going up. What's keeping most of them from leaving? It's the forces of attraction between them. But some of them are at higher temperatures than others because not all of the molecules have the same kinetic energy. We just talk about the average kinetic energy is related to the temperature. So at any given temperature, you can have some molecules that are very energetic and some that are very not energetic. So if you have the energetic ones headed towards the surface, they have enough kinetic energy to break loose and go into the gas state. You guys heard of the game called Red Rover? Got one nod. Yeah. Pretty soon this analogy won't work anymore because they don't let kids play this at school anymore. So I'll explain Red Rover to you. So you get two groups of children separated from each other by like a grassy field or something, and they make two lines and they hold hands. And then somebody on one team says, Red Rover, send Sally right over. And so Sally from the other side runs to this side and tries to break through the line. You can see how wrists could get broken, right? Yeah. We survived. They don't let kids have any fun. Anyway, what's going to determine whether Sally gets through that line or not? The strength of the grip of the people in the line, right? And also how big and how fast Sally's running. If Sally's a little tiny kindergartner, she's not going to have much impact, right? But, if Sally's a 6th grade softball player and, she's running fast and she's more likely to break through, right? So I see the surface of this liquid as being like a Red Rover line. And here's Sally down here being sent right over. Well, when will Sally be able to get through the line? If Sally has enough kinetic energy to break through. So we have the strength of the attractions here, that's like the hand strength of the Red Rover line, versus the kinetic energy of the individual particles. So, two words that we should know. Vaporization means going from a liquid to a gas. Condensation means going from a gas to a liquid. Any questions? So here's some pictures. A picture, a graph. This is looking at the fraction of molecules that have a given amount of kinetic energy. And so we see there's a distribution of thermal energy. We can say, well, this is the average kinetic energy that's related directly to the temperature. But at any given temperature, you've got some that have a high energy and some that have a low energy. And of course, most of them are somewhere in the middle. What happens as you heat up a liquid is that this distribution moves up, but it also broadens out. And so here, this line represents the kinetic energy needed to break through the Red Rover line to escape, to evaporate. So at a higher temperature, more of the molecules are going to have enough energy to break loose. At higher temperatures, vaporization occurs more quickly. We know this from real life experience. Which is going to dry faster? Something drying is the liquid water evaporating, right? So you got a wet towel. Leave it on the bathroom floor or put it in the dryer. Duh, put it in the dryer, right? So apparently a lot of children don't know about this because they leave their towels on the floor. Why does it dry faster in the dryer? Because there's heat. Evaporation happens faster at higher temperatures. Another way we can increase the rate of vaporization is to increase the surface area. In order for molecules to vaporize, they have to get to the surface, right? So if we have more surface area, we have more particles that have a chance to escape, right? So an illustration of this would be, let's say you take 2 glasses of water and you just leave one on the counter and the other one you dump on the floor. You just, same amount of water, spills, runs all over the place. You go away. Maybe mom's on vacation. Come back later, which one's going to have evaporated away sooner? The one that's all spread out on the floor or the one in the glass? The one that's spread out on the floor, because it has larger surface area. This is also why when you're using a hand dryer, you want to rub your hands together, make sure that you're getting your maximum surface area for all those molecules. The heat helps by giving them more kinetic energy. I still think they don't work nearly as well as a good paper towel. So if we have a liquid with strong intermolecular forces, it's going to evaporate more slowly. So oil, even though it's nonpolar, has strong intermolecular forces, like I mentioned before, because of the size of the molecules. So if you have some oil and some water, is the oil going to evaporate like the water does? Why not? Because it's held too closely together, too strongly together. It's not going to evaporate at room temperature. It's got stronger intermolecular forces. So we have words to describe that. Volatile means a liquid that will vaporize easily. Non-volatile does not vaporize easily. We heard this word back when we did experiment 6A, molar mass of a volatile liquid. And we put that liquid in a flask and we heated it and we saw it evaporate and go into a gas. It looked like it disappeared. Right? That happened easily. That experiment would not work with just any old liquid. There is energy involved in the vaporization. So if we think again about that beaker of water, if the beaker of water is insulated, so no heat can come in from the outside, what's going to happen to the temperature as the water evaporates? Well, there's this distribution of kinetic energy, right? Is it the high kinetic energy or the low kinetic energy molecules that are going to evaporate? It's the high ones, right? So we've got the higher kinetic energy molecules escaping. What does that do to the average kinetic energy of what's left? It makes it go down. It makes the temperature of the water go down. Vaporization is an endothermic process. It involves taking in energy. This is why we sweat when we get warm, because the sweat, the liquid on our skin, then can evaporate, and as it evaporates, it cools us because it's taking away those high energy molecules. The opposite of vaporization is condensation. Condensation is an exothermic process, which is not necessarily obvious. We should be able to just think about it and realize that evaporation is endothermic. What can we do to make evaporation happen faster? We could heat it up, right? We could put energy into it. It's endothermic. So if that's endothermic, the opposite has to be exothermic. And if you've ever held your hand over a pot of boiling water, you probably took it away very quickly because it felt extremely hot. Why is that? That's because the steam coming from the boiling water hitting your hand that's cooler condenses, and when it condenses, it releases a lot of energy into your hand. The energetics of vaporization also have a big effect on climate. These are some numbers I gathered up. Average daily temperatures in July from 1971 to 2000, for Fresno and San Francisco. So Fresno, average high temperature, 96.6 Fahrenheit, sounds about right. Low, 66. So a temperature difference during the day of 30.5 degrees. And we all know, yeah, that can definitely happen. You were wearing shorts and a tank top and you were dying, and then later you're freezing, right? And so no matter how you dress, you're going to be uncomfortable part of the day, right? Always bring a sweater. In San Francisco, the average high temperature in July is 68 degrees. That's cooler than it is in this room right now. The average low is 54. The difference from day to night is only 13.8 degrees. The temperature hardly changes at all. San Francisco is only a little bit north of Fresno, so it's not like we're comparing something in Alaska or anything. What's the difference? Water. San Francisco is surrounded on three sides by water, the ocean and the San Francisco Bay. Here in Fresno, normally we don't have a lot of water, right? Right now our rivers are flooding all over the place, but that's another thing. So we don't have any large bodies of water. We also don't have much humidity in the air. Humidity in the air will also moderate the temperature changes. Because what happens in San Francisco, the heat of the sun comes down and it heats up the water, right? Causes water to evaporate. That's absorbing energy, right? And then when the sun goes down, the water condenses again, and that's releasing energy. And so it moderates the temperature. Any questions? So, of course, being chemists, we want to quantify all of this. So we call this the heat of vaporization. Remember, the heat really is enthalpy, but heat makes more sense because that is an H, right? So heat of vaporization, this is the amount of heat that's needed to vaporize 1 mole of liquid at the boiling point. So the chemical equation here would be H2O liquid going to H2O gas. In order for 1 mole of that to evaporate, it's going to absorb 40.7 kilojoules of energy. The heat of vaporization is always going to be positive because vaporization is always an endothermic process. It will depend a little bit on temperature, but not a whole lot. So here we've got water, chemical formula, boils at 100 degrees Celsius. So delta H at the boiling point is 40.7. Delta H at room temperature is 44. It's a little bit higher, but not very much. When a substance condenses, the same amount of energy that was absorbed to evaporate it is released when it condenses. So we don't talk about a heat of condensation. We just recognize that the heat of vaporization, change the sign, that's the heat that's released when 1 mole of gas condenses into a liquid. So this is like the heats of reaction and things that we saw in previous chapters. This can be used as a conversion factor to relate amounts of reactants or products to the amount of heat involved. So calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. And before I forget what it is, I'm going to write down the heat of vaporization. So we've got liquid water boiling going into the gas state. Delta H for that reaction, that change, is 40.7. So if 1 mole of water is converted to gas, 40.7 kilojoules of energy have to go in. So this is a kind of stoichiometry problem. It's all just dimensional analysis. So what they gave us here is 2.58 kilograms of water, and they're asking for heat in kilojoules. So we're starting with the 2.58 kilograms of water, and we're trying to end up with kilojoules. And the hard part is, how do we get from one to the other? Well, the heat of vaporization relates kilojoules to what? Moles. So if we had the moles of water, we could find the kilojoules, right? How can we get from kilograms of water to moles of water? We're going to use the molar mass, and then the molar mass is going to be in grams, so we'll need to convert to grams, right? So we figure that out, and then that tells us what to do. 2.58 kilograms. If you haven't mastered dimensional analysis yet, it's not too late. So I've got 3 arrows there. I'm going to have 3 conversion factors. Kilograms to grams to moles to kilojoules. This unit comes to the denominator of the next term so that the units cancel out. I have analyzed the units, the dimensions. Now I put the numbers in. It doesn't matter what order we do them. This one looks easy because the number's just sitting there. 40.7 kilojoules for 1 mole of water. So kilojoules is on the top, so I put the number on the top with the kilojoules. Grams to kilograms. So there's a gram on both sides. This side has kilo. What does kilo stand for? Times 10 to the 3. So on the bottom, I've got 1 kilogram. On the top, I have 1. I'm going to write what it means, times 10 to the 3 grams. And then in the middle is the molar mass. So I happen to remember that one. It's 18.02. But you could always just calculate that. So 2.58 times 1EE3 divided by 18.02 times 40.7 Anybody else get that number? Yeah? Okay. I've been making a lot of mistakes lately. It would really only have 3 sig figs, so probably be best expressed as 5.83 times 10 to the 3 kilojoules. But that's the amount of energy needed to vaporize 2.58 kilograms of water. Of course, the other question is, why would anybody want to know that? I have no answer for that. Any questions? So we talked about vaporization and condensation in an open beaker. What if the container's not open? What if we have an Erlenmeyer flask here and there's a stopper so that the water that gets into the gas state, it has escaped the liquid, but it can't get out of the container. So as these particles evaporate, what are they going to do? What do gas molecules do? They travel in straight lines till they bump into something, right? And then they bounce off until they bump into something else. And so these water molecules, this guy might go up here and go bong, 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 bong. Eventually, they're going to collide with the surface of the water and get trapped again. So we have 2 processes here. We have water evaporating. That's going to depend on the temperature of the water and the surface area of the water. And then we have condensation happening, Condensation is going to depend on how many gas molecules are up here. We could think of that as the concentration or the pressure of the gas molecules. Initially, we have no gas molecules up there, so there's no condensation happening. All we have is evaporation. Evaporation is just going to happen at a standard, a constant speed here because we're not changing the surface area, we're not changing the temperature. So evaporation just chugs along, evaporating. As that happens, we get more and more gas particles up here, and so the rate of condensation increases until at some point the rate of evaporation is equal to the rate of condensation, and we reach dynamic equilibrium. It's dynamic because molecules are still evaporating in condensing. But it's an equilibrium because the amount of molecules in the gas state is not changing. They're just switching places. So this is looking at that as a graph. So here we have the rate of evaporation. In that container, it doesn't change, it's just constant. The rate of condensation of the gas molecules getting trapped is going to increase as we get more and more water molecules in the gas state. Eventually, it's going to meet up and match the rate of evaporation, and at that point, it looks like nothing's changing. We've reached dynamic equilibrium. The pressure of the gas there is called its vapor pressure. Vapor pressure will depend on the strength of the intermolecular forces because the rate of evaporation depends on the strength of the intermolecular forces. If those particles are held together very weakly, they're going to evaporate more and you're going to get a higher vapor pressure. So weak forces give us high vapor pressure. If we disturb this system, it's going to respond in a way to minimize the disturbance. That's called Le Chatelier's principle. So here we have a system in dynamic equilibrium. The rate of evaporation, the rate of condensation are the same. If we pull this plunger up, increasing the volume, what does that do to the pressure of that gas? The pressure is lower, right? Or we could think of the concentration, how many molecules per liter. The concentration is less. Well, is that going to affect the rate of evaporation? No. But it will affect the rate of condensation, right? Because these guys are bopping around in a much larger area now, they're not going to crash into the liquid as frequently, right? So condensation is going to be down. So what's going to happen? Well, the rate of evaporation is still going on, and as that keeps evaporating, we'll get more and more gas here until we reach that equilibrium again, and the pressure here is going to be the same as there because it makes up for it. If we decrease the volume, increasing the pressure, now we increase the rate of condensation, and again, they're going to go to where they are equal to each other. So the vapor pressure will be constant at a given temperature. So what happens to the vapor pressure of a substance when its surface area is increased at constant temperature? Well, let's say we had a tall, skinny container and a short, wide container, and they both have water in them. Larger surface area, smaller surface area. Does surface area affect the rate of evaporation? Yeah. If you spread the water out on the table, it'll evaporate much faster than if you leave it all balled up together in a glass, right? So the rate of evaporation is going to be greater here. Does the surface area affect the rate of condensation? This is a much larger area, right, for those molecules to crash into. a bigger target than over here. It also affects the rate of condensation. So how's the vapor pressure going to be affected? It's not. Because the increase in evaporation and the increase in condensation cancel each other out and the vapor pressure stays the same.